I have posted on Canvas the assignment or the classwork, this one, so you can download it. And there are two different, okay, so we have two different exercises. The first one, you can do it right away. So, okay, let's do it. Work on this one. You have to work with your ID number. Okay, so if we have an X, this is the last figure of your ID. If you have a Y, it's the second last figure of your ID. So basically, we have to work with a building in Keene with a daily hot water usage of 100 and 100 and something gallons. The slope of the collectors is 30 plus this number, it can be 31, 32, 33, whatever. The size of the tank is 2 gallons per square feet. Okay. So the first question is, what is the water set temperature and why? Well, the answer to this question is always the same. The water set temperature is 140. Why? Because we have to kill the Legionella, these bacteria. Okay, so the domestic hot water in buildings, usually it's always 140. It can be more if we have other requirements, but for residential and commercial buildings, usually it's 140. And now, what is the number of collectors and the area in feet square if we want the yearly F factor of 0.6? And finally, what is the auxiliary fuel energy per year? We have to open F chart. So remember that we don't want economic analysis. Make sure that it's in English units. The system, we have to select the first one, active domestic hot water. Collectors, it can be flat or evacuated. Last time we worked with a flat plate. Today we're going to work with this one, with the evacuate tube. This is the heat pipe, more efficient, more beautiful, more expensive. The weather location, let's work on northeast. And that's it. Now we have to go over this. The water volume per collector area, it's 2 gallons per feet square. Okay. The fuel, let's work with gas. The efficiency of fuel usage, if we don't have any information here, okay, so we can leave the default values. 70, it's a little low, but that's fine. The daily hot water usage, here we have to change it because we do have, so it's 100 and something, depending on your ID number. Okay, so we have to type here 100 or whatever. Then the water set temperature is always 140. The environmental temperature, if they don't say anything, we assume that the hot water tank is indoors. So if it's indoors, and if it's in the kitchen or if it's in a mechanical room, okay, but we can assume that it's indoors and the temperature is close to comfort, 68 or 70, whatever. And all these elements, let's leave. If we don't have any information, we will have the default elements. I explained last time what this was about, okay? But you can leave these numbers. Then the number of collector panels. This is what we have to find out. This is the second question. So what's the number? We have to try something, 26. It's gonna be too much, I think. The collector panel area, we can leave this. When we select a collector, we will have specifications, and then we will have the area of that panel, but we can leave this. And then all these elements depend on the efficiency of the collector. Again, we need to go over these specifications, and we will have all these parameters, FR, UL, FR, tau, times alpha. So that depends on the efficiency of the collector. The slope is here, so it should be 30 or 30 something degrees. So let's say 30. The azimuth, well, I don't recommend you use this kind of technology if it's not south oriented. So let's say that the azimuth it's always 0, it's south oriented, and the slope is 30 degrees. And then the incidence and factor. Okay, so we can leave this, and the only thing we have to try the number of collectors, because we want the F value to be 0.6. Sorry. I don't know how many collectors you have. 26 is going to be too much. Let's try 10. I think 10 it's going to be too much too. But let's run, calculate. And here you see that the yearly value is 0.85, but here we have a lot of 1. Okay, so that means that in summer we might have trouble of overheating the system. Okay, so that's why setting a goal of yearly 0.6 F value, it's good, because that means that in summer we won't have problems when it comes to overheating. Okay, so what can we do? We can reduce the number of collectors. Let's start with 5 and then run again and calculate. Okay, so now we are getting there. The yearly value it's 0.59. It's almost 6, and here we don't have any value of 1. So I think we can afford another collector. 6. Calculate. Okay, so now we are above 0.6, and these values are 0.9, 0.9. Okay, so we don't have risk of overheating the system. So that's very easy. We always, what's the number of collectors in the area in square feet? We are working with 6 collectors times 20.8. Okay, so the solution, so the answer to this would be 6 collectors times 20.82 square feet per collector. So what's the total area? 6 times 20.82, whatever. And what's the auxiliary fuel energy per year? We have to go, this is the yearly value, and this is the auxiliary energy. So we need 10,000, no, it's 10.2. Be careful with the units here, because it's 10.2 times 10 to the power of 6. BTU. So this number is 10 million BTUs. How can we turn this into therms? The unit therm. How many BTUs do we have in one therm? 100,000. Okay, so 100,000. So it's 10 to the power of 5. If we divide this, so I think it will be 102 therm. Okay, so if you tell your client that you need 10 million BTUs, the client will be scared. But if you know it's only 100 therm, oh, 100 therm sounds good. Well, it's the same that again, having this million number, it will be something scary. So that will be the, so it's just like this. It's very easy to calculate the domestic hot water. We only need to know the hot water usage, the slope of the collectors, and then we need the specifications of the system. But either if we use the most efficient system or the less efficient system, probably instead of 6 collectors, if we have a better system, we will need only 5. Or if we have a worse system, we will need 7. Okay, but it's around 6. And collectors are not quite expensive. What's the price of a solar collector? So let's go to my reference, my favorite page on Earth, which is Alibaba. And here we can solar thermal collector. So do we have it's just the price of the system, solar thermal collectors. Here we have PV panels. Okay, those are solar, but this is not a PV. I would like to find the heat pipes. Okay, so here we have the heat pipes, the evacuated. Okay, it's Amazon. Okay, let's trust Amazon. So here we have 1,900, so almost 2,000. But what does it mean? We need to find out if this is just the panel. This is not the panel, so probably this is the system. So it includes the panel, the pipes, the water tank. Okay, so probably, and it's certified. So, but I would like to find, okay, so here, no, that's it. We have 15 tubes or 25 or 30 tubes. When we are working with these heat pipes, we are not working with area, we are working with tubes. Okay, anyway, we need to know how many tubes we have in a square feet or this. But okay, if we have 15, the price is only only 1,200. If we have 30, we have 2,000. So that's the price. But I would like to know if that includes the, yeah, I think, look at this, buy it with, okay, so we have some, we have the pump here. Well, we can have, I think this is the price of just the pipe, the tubes itself. It's quite expensive. Okay, 30 tubes. No. Let's try to find a price for this thermal collector, and that makes sense. Okay, so a thermal collector is around $100. Yeah. So if we have a 20 square feet, is around $100. So that's the price of this kind of. So adding one more, it's just adding $100 more to the system. It's not a big deal. Okay. The other ones are more expensive. Those ones are more expensive. They are better. They are more reliable. Probably they have fewer problems with freezing, but they are more expensive. Okay. Anyway, this technology, the flat collector, is it's quite cheap. Okay, so we're talking about $100 per panel. It's not a lot of money. So that's it. Okay, so we need around 6 collectors to do this. So do this with your numbers, with your ID, and just let me know here. If we want to make it better, probably we can plot or we can print here things from the PV chart. Okay, so I think having this summary will help. Okay. If we have this as a summary, it helps. And I don't know, if you place here the area of collectors. And what's the other information we need? Oh, the auxiliary. Oh, and it's something important because depending on the area of collectors, we have the volume of the water tank. The volume of the water tank is 2 gallons times the area of collectors. So what is this? 6 times 20, 6 por 2, 12. Me llevo una, 6 por 8, 48 y una 49, y 4. So this is, I'm not wrong, this is 124 square feet. So what's the volume of the tank in gallons? It's 2 gallons times 100 the area of the collectors. Okay, so basically this is all we need. We need the area of collectors, we need the volume of the water tank, and then we need pipes. Yeah, we need a plumber who works with this. So we have the collectors on the roof. Probably the water tank is on the basement or somewhere else, and then we need to connect with the pipes, the collectors, and the tank. And this is the schematic view. Then we need a boiler. We need an auxiliary system in the event that we can't have 140 Fahrenheit. We need to connect the tank to another auxiliary system, a gas boiler or whatever, and that's it. Okay, but this is the information we need when we are calculating that, the area of collectors and the volume of the water tank. So what's next? The next classwork is we have to add a heating system. Okay, so we have collectors here, and then we have a tank. We have domestic hot water at 140 Fahrenheit, and then we have a system, a radiant floor system, radiant floor heating system with, and usually the radiant floor temperature is not 140, that's too hot. Radiant floors are between 90 and 100 Fahrenheit. Even 100, it's too much. So maybe it's closer to 90 than to 100. But well, from 85 to 95, it will be okay. But now we need to understand the schematic view of this. Okay, so. What is the system? We have solar collectors, and all the solar collectors are connected to this tank, to this buffer tank. This is the water supply, because this is the water that we're using in the shower. So the tank gets empty. So we need a water supply from the grid, from the water grid. Okay? So when it goes down, we fill the tank up again. We connect the solar collectors to the lower part of the tank. Why? Because hot water tends to go up. Okay, so if we want to get this water at 140, we have to take it from the top of the tank. Okay, because the hottest water will tend to go up. So the hottest, if we need to get this water at 140, we need to get it from the top of the tank. So that's why we have this pipe going to the shower, always on the top. And we have this heat exchanger that comes from the solar collectors, always at the bottom. So the solar collectors are heating up this, and the water, the hot water, is going up, and the cold water is going down again. If we need to supply water, the water that we supply is cold, so it has to be at the bottom. If we supply this water at the top, doesn't make sense, because we are mixing cold water with the hot water that we needed. Okay, so everything that that has to do with cold water, it has to be at the bottom of the tank. Everything that has to do with hot water, it has to be at the top. Then where do we place the gas boiler? We need the gas boiler, an auxiliary gas boiler, and this gas boiler is always placed at the top of the tank. We have the same thing here. Okay, so the water, the solar collectors are connected to the bottom. The auxiliary system is at the top of the tank, and we always get water from here. Okay, So those are small details, but if you don't do this correctly, people will not take you seriously. Okay, so he has connected, or that guy or that architect has connected the gas boiler to the bottom and the water supply is at the top. Doesn't make any sense. Okay, so those are small details, but plumbers know what to do. So even if you provide them with the wrong drawing or schematic, they know what to do, but it doesn't make a good impression if you don't do it correctly. Okay, so we have a gas boiler, and as you can see, this gas boiler is connected to the radiant floor here, to the heating system, and we have a lot of connections. So as architects, probably we don't need to understand that. This is more for plumbers, okay? Because the plumber needs to understand what pipe is connected to what. And we have different elements here. We have the solar collectors, the tank, the gas boiler, and the radiant floor. And we have the shower or the domestic hot water. So we have different temperatures here, and each device has to work at different temperatures. So the radiant floor is working at a different temperature as the shower, for example. So that's why we need this flexibility. So sometimes the gas boiler will be heating up the water tank up to 140, and sometimes the gas boiler will be heating up the radiant floor, but only up to 100. And keep that in mind. When we are working with a heating system, especially a radiant floor, the heating system is working for hours. Okay, so I don't know, but if we turn on the heating system in the morning, probably we will keep it on until the evening. If it's cold, it might be working 24 hours. But we don't need hot water 24 hours a day. We need hot water just when we are taking a shower or when we are washing our hands. So it doesn't happen 24 hours a day. It happens 20, 30 minutes, 1 hour. So if we know so knowing the habits of people, it's important to save energy, because if we know that this family uses the shower only from 8 a.m. until 10 a.m., we only need 140 Fahrenheit these 2 hours. In the event that they have to take a shower at noon, okay, so the gas boiler can start working, but that will happen only maybe 1 or 2 days a year or a month. So knowing habits, it's important, because we can have the gas boiler heat up the water tank only for 2 hours, and then the rest of the system, the rest of the time, we only need 100 Fahrenheit as a temperature. Okay, so those are the kind of things that we need to know. And it depends on the use of the building. It depends on the family or the client. So if we have a building like this, here we don't have showers. We don't have showers. We use domestic hot water just to wash the hands. So it's not a big deal. So that's why the water tank we have here in this building is not that big, because we don't have showers. In the recreation center, I'm sure that the system will be different, because they are using showers there, and we don't know. It depends on if we have a game or if we have people using the gym. I don't know. It depends on many things. Okay, so building like that will be complicated to understand. But when it comes to single family houses, it's quite easy, because people have habits. And I don't know if you realize that we always do the same thing, kind of. Okay, maybe on the weekend we do something different, but the rest of the time we have habits. So if we control this and we can communicate this to the plumber or the one that it's dealing with this, it saves a lot of energy. And so this is what we have to do. Anyway, that's the system. So that's an option. There are different options, and that's why I have this lesson. Okay, so this is the best option for domestic hot water, and just domestic hot water. This is option 2, and this is what comes from F chart. Well, this is nicer because we have colors, and here we don't have colors, and but we have to try to understand this. Where does it come from? So that's interesting, because in the F chart, you see that we have help here, and we have the manual. So you can click here, and can you download the manual if you click there? Nope. In my computer, in my office, I could do it. So I don't know what's wrong with this. Probably, is it the manual here? This F chart, it's not. See, F chart software. F chart manual. Okay, so if you come here, we can download this and zip. Oh, I will unzip it in the desktop. Okay, so I have it here. By hambre. Okay, so you can download it from the website directly, but in other computers, if you just click here, you are directed to the website. Anyway, we have the manual, and here we have different, it explains what we have. Okay, so it explains the commands, the economics, and here we have the system and output descriptions. So this is the domestic hot water. This is the first one. And then the second option, here we have the people bed storage space. We're not going to use this one. And we're going to use the water storage space and domestic hot water system. Okay, so here we have heating and the domestic hot water. So if you click here, the 4.3, we have the information about this. And here we have the schematic view, and here we have the output. Okay, it explains what all this chart means. But I want to focus on this. I want to focus on the schematic view. So what do we have here? We have different options. And again, there is not, if there were a better option, everybody would do the same. But we have to connect different things. We have to connect, this is the house, okay, the room or whatever. This is the solar collector, and we have a main storage tank. But here we have a preheat tank, okay? So what is this? We have a solar collector, we have the heat exchanger, and this solar collector is connected to the main tank. Then the main tank is connected to the preheat tank, and the water supply is on this preheat tank. And then we go this way, and we have another service hot water tank, and here we have the auxiliary element. And here in the house, we have another, in the room, we have another auxiliary source of energy. What do we have to, and we have a relief valve here. The relief is the expansion tank. Okay, so we always have an expansion tank. When we have a closed loop and we are dealing with hot water, we always need the expansion tanks. So in this schematic view, we have three tanks, 1, 2, and 3. I think it's too much. And then we have another system that goes to the house. So probably this house is the radiant floor or the radiators. And then we have an auxiliary element here. What does it mean? I think it's too complicated, but what we have here is domestic hot water, because here we have the hot water tank. Okay, so this goes to the shower. And we have another pipe that goes to the house. How can we do that? Or how can we turn that into something more reasonable? Okay, let's do it. If we work with the main tank, okay, so this is the main tank. We work with solar collectors. This is the solar collector. And then I want to go from the solar collector to the water tank. Okay, and from the water tank to the solar collector. There you go. So let's make it thicker and thicker. If we want, if it's hot water, so let's use a red color. And if we have supply and return or inlet and outlet, if we have an inlet and outlet, we can use the dashed line for this one. Okay, so this is it. We have solar collectors and the water tank. So the solar collectors are connected to this water tank. The heat exchanger is here. Okay, so that element that we have in the schematic view, the heat exchanger is this element we have here. This is the heat exchanger. So it's within the tank. In our schematic view, the heat exchanger will be here within the tank. Well, if we use, okay, so with this is the main storage tank. And now we need another preheat tank. Okay, let's do it. So there's another tank here. And there's another connection between this tank. It has to be red and thick. And here we have another one. So there's an inlet and outlet. So that would be dashed. Okay, so there's another heat exchanger. Here we have another tank. So we heat up this tank, and then there's another connection here. We are using this warm water to heat up, to preheat this tank here. On the other hand, we have the water supply here. Okay, so this is water supply, and this water supply is cold. So this is not red. This is the water supply to this tank. And then from this one, what else? We have another pipe or another pipe going up to this service hot water tank. And here we have the auxiliary element. So there are 3 tanks here. Okay, let's do it. There's another tank here. Let's make it smaller. And this is not cold because this is warm water now. So we use this. We change the weight. We change the color. Okay. And now here we have an auxiliary element. So there would be something different. This can be the boiler okay, this is the boiler, and this boiler again is heating up this tank. So we always need the inlet and outlet from the boiler to that tank. And now from this tank, we at last, we can have the domestic hot water. Okay, from this one, we go to the shower. Okay, so this is it. We have solar thermal collectors. We have a tank. We have a second tank. In this tank, we have the water supply. And then there is another tank here, and we have the boiler connected to this hot water tank. So the temperature here would be 140. We have shower. So the temperature here will be 140 Fahrenheit. What else? So there's another heat exchanger connected to the main storage tank, and this is connected to the house itself. So this is not a tank, this is the radiant floor system. So let's do it. So from this one, I'm going to do it here because I think it would be better. Okay, so this circuit is connected to the radiant floor. And I'm going to bring something from a picture. Okay, so this is the radiant floor of the room. And is that all? No, it's not, because according to this schematic view, we have an auxiliary element here. So this auxiliary can be we can have a heat pump. And this heat pump can be connected to a split unit. An indoor split unit. Okay. I think it's too complicated because here we have 3 tanks. Why do we need 3 tanks? We don't know. 1, 2, and 3. Well, we control the temperature. It's good that we can control the temperature because we can have a temperature in this tank, and this temperature can be connected to the radiant floor system. But here with this, we can control this temperature to be connected to the shower. So we need a small boiler to heat up this tank if we need it. And but if we don't have enough temperature here on a cloudy day, we don't have anything. On a cloudy day, we don't have enough temperature either for the domestic hot water or for the radiant floor. So on a cloudy day, probably the heat pump with the split system will be working. We don't have any sun, with the radiant floor is not working. The shower, we need 140 Fahrenheit. Okay. So the boiler, if we don't have anything from the solar collectors, the boiler will be working and it will heat up this little tank up to 140. The temperature here, the temperature inside the room can be, I don't know, 90 Fahrenheit. Not inside the room, but the water running through the radiant floor can be 90 Fahrenheit. Okay, so this is it. It's too complicated. So if we want to do something like that, I will try a different option. Okay. So imagine that we simplify this and we just have one tank. So we can bring this boiler here. And the shower can be like this. Okay, that's easier. We have we need the supply, the cold water supply. Here. Okay, we have a tank. We use this tank for the shower. If we don't have 140 Fahrenheit, we can use the boiler. Okay, so we have energy from the solar collectors. If we don't have enough temperature, the boiler is connected to the top of the tank. So it heats up only this part of the tank, this top of the tank, up to 140. The temperature at the bottom of the tank will be lower. So we connect this temperature to the radiant floor. If we need an extra energy, we can have a very cheap heat pump with a split system inside the room. Okay, so that works. I think it's not because I have done this, but I think this is too complicated. The more the tanks, the more devices you have, the better, because you can control more things and you can add other strategies. But I think there is no point of having 3 tanks. But this is the system that they propose. They propose a system with 3 tanks: the main storage, the preheating, and the service hot water tank. Okay. But my option would be this one. With just one tank, we have everything we need. There are more options. So let's do this. And I don't want a heat pump. Okay, so I don't want to regulate the temperature of this with a split system. We have solar collectors. We have a tank for the domestic hot water, and then but now I want to use 2 tanks. Okay, not 3, but I want to use 2 of them. So I have another tank here. I connect the radiant floor here with a different tank, And since I'm going to have different temperatures, okay, because I need 140 here, is this connected to these solar collectors? I will use another set of solar collectors to be connected to this tank here. Okay. And what if I don't have enough energy because I don't want a heat pump here, I just want the radiant floor. What if the temperature is not enough? Okay, I can connect this boiler to this tank. So I think this is what I would do. Okay, I'm going to use two tanks. This tank has to be at 140. Okay, the temperature on this tank should be 140. The temperature of this tank should be 90. And we have a boiler, so if we need 140, the boiler is heating up this one. If we need 90 here, the boiler is heating up this one. But we can control two different temperatures for this and that. And I have some solar collectors connected to this tank and some solar collectors connected to that tank. So those tanks are different in volume because this is 2 gallons per square feet and this is 2 gallons per square feet. So basically we are working with two different systems. I have the domestic hot water with this system. I have another heating system with the other one, two different tanks. Probably this is smaller than this one because the heating load or the power that we need for the domestic hot water is less than the power that we need for the heating system. And we have an auxiliary boiler. If we have enough sun for both systems, probably the boiler is not working. If we need an auxiliary heating for the domestic hot water, the boiler is connected to this. If we need something auxiliary for the heating, the boiler is connected to that. And if we need both, the boiler is heating up both tanks at the same time. So here, probably here we have a big tank because we have a lot of panels connected to this one. Here we have a small tank for the domestic hot water, a bigger tank for the heating system. And with this one, I have 3 tanks. I don't see the point of having 3 tanks, but I'm sure that there should be a reason for that. So again, we have to talk to people. These are the 3 proposals. Probably some of there will be a proposal that it's the best in terms of energy efficiency, but probably would be the most expensive one. Then there's another proposal that it's not that efficient. It's not about efficiency, it's about flexibility. The more tanks, the more devices you have, the more things you can do. But and sometimes you have a building and you don't know what you're going to do with that building. Maybe the building will change the use in the near future. It has to be flexible, that's fine. But if you are designing a single family house and the family has the same habits every single day, then you don't need flexibility. You just need to do what is the best option. Okay. So anyway, we have the schematic view. Okay, so this is a view in which we just have a tank. Yeah, I think this one is, well, that would be a 4th option because that would be my best option, but with just 1 tank. Okay, that's fine. But again, I'm not a plumber. I'm not responsible for installing as an architect. I mean, I'm not responsible for the installation, and probably there are companies that are doing this. You have to talk to them. Okay, so what do you do? What do you usually do? Well, we do this. How many tanks? 3 tanks. Why? Because we have this option, this option. Probably, if you don't know anything, they will try to sell you all their products. Okay, so if they have 3 tanks, they will try to sell you or your client 3 tanks. Why? Because they make money out of it. Maybe they are necessary, maybe they are not. And then they will try to sell you a heat pump with a split system and a radiant floor and a gas boiler. And what if we have an electric boiler just in case? Okay, that's fine. You will have the best system on earth. It will be very expensive. And they are trying to make money. So we have to understand the companies. They try to sell all the products. And the more complicated the system is, the more products they sell, the more money they make. But probably the system is better. Okay, but do I need this? It's like, imagine that you have, okay, I need a car because sometimes I drive alone to the Stop and Shop and I buy a Kiwi. So I need a car for that. So I need just a small car. But what if I have 7 children and one day we gather all the family and we go on an excursion? Okay, so I need an SUV with 7 seats. But what if I go to the church with my wife? Okay, so it's just the 2 of us. So I need another car that has only 2 seats. Okay, that would be great. You are filthy rich. You have a car for each day of the week. That's perfect. But what if you can't afford it? You need just 1 car. Okay, so what do we need? I have a wife, 7 children, so I need a big one. If I only can afford 1. So the same thing happens with the system. You can have anything. Okay, so if you are filthy rich, I can have a system for winter, another system for summer, or I can have a different system for each day of the week. Perfect. Enjoy. But if you have to decide, you have to make decisions and you have to cut down on options. Okay, so what are you doing 90% of the time? So go for it. So this is the schematic view. When it comes to calculations, it doesn't really matter the schematic view. What we need to know is whether we have just domestic hot water or we have the heating system. So let's go for the heating system. The second exercise is this. Okay, so we are using solar collectors and we have domestic hot water and the heating system. So the first thing we need to know is to calculate the heating loads of the building. We are going to use the Excel file to calculate very quickly the heating loads of the building. We can do the same thing with Revit. Okay, so we have the heating loads. We have used a software to calculate the heating loads of the building. And now we have to introduce this data into the F chart. We can use Revit, we can use more advanced software, or we can use the Excel file that we have used before. And it's not there. Yes. Okay, so we can use here the data. This is what you have to do. The R value of the wall has to be above 40. The R value of the floor has to be above 20. The R value of the roof has to be above 70, sorry. We have done that. It depends on the thickness of the thermal insulation. So you have to provide me with a detail in which you show me that you have these values. Okay, I don't mind what you do, but at the end, those values, the R value of the wall should be about 40. So I'll change this. 39. Okay, so this is 45. That's fine. What's the? But I don't mean that you have to do this detail. It's up to you. I'm just. Then the area of the walls is 1,000. So the area of the walls is 1,000 square feet. Now the floor has to be above 20. So probably I can reduce this 29, 24, okay? So this is above 20. The area of the floor is 2,000. No, this is the floor. And the roof has to be above 70. This is 68, so I have to increase the thickness of this. Okay, now it's 72, and the area is 2,000. Okay, I don't mind, but you have to copy this. And on the final report, I need to know that you have a wall that is, okay, the wall is about 40, and the area of the wall is that. Okay, so you have to do this with the wall, the roof, and the floor. What's next? The U values of the window. So we have north and south windows. The area of north windows is 80. The area of southern windows is 120. The U value is 0.26 and the solar heat gain coefficient 0.5. So you can go to this. The U value of the window is 0.26. The area of the northern windows is 80. The solar heat gain coefficient is 0.5. Okay, so this is 0.6. This is 120, the south, and this is 0.5. In the rest of the elevations, east and west, the area is 0. Okay, so here we have the total load of the windows. So again, you have to copy the north and south. So this is the chart of the windows. So I have to check this, that the U value, the solar heat gain coefficient in the area of the windows is the correct one. What's next? Ventilation, I think. Yep, ventilation. Well, the first indoor minus outdoor temperature should be 70 minus 0. Okay, so I have to go up at the beginning, and this is 70 minus 0. Then ventilation, we have 10 people, a 50% efficient heat recovery. So the heat recovery is 50%, the number of people is 10 people, and the CFM per person, it's always 20, okay? So here we have the ventilation loads. And what about the infiltration loads? For the infiltration loads, I have had this test, the blower door test. So the result is 2, very good, very tight building. The N is the exposure. Okay, so you remember that there is a map. We have a zone, a wind zone. Then we have the exposure, exposed or protected or shielded or whatever. So this is the result that we get from the blower door test, and this is the exposure, 2 and 18.5. So the this result from the blower door test is 2, and this is 18.5. I need the volume of the building. The volume of the building is 20,000 cubic feet. That would be 20,000. Okay, and we don't need anything else. And this is the total ventilation and infiltration load. Anything else? No. Okay, so now we need the number of collectors in the area in square feet. If we want a yearly F factor of 0.3, if we are including the heating system, having an F factor of 0.6 is going to be difficult because we're going to need a lot of solar collectors. Okay, so the goal, if we're including a heating system, having a 0.3, it's quite good. And then we have to plot the heat load the domestic hot water, and the F. Okay, so we have to plot these things. So now we have to turn to to the F chart. We have to select a system that includes water storage. The third one, water storage and domestic hot water. We are in the northeast. The water volume to collector area, it can be 2. And this is what we have to do now. This is the building UA 0 if it's only domestic hot water. We have domestic and heating, okay? So what is this UA? You remember that the heating load is U times the area times indoor minus outdoor temperature. And here we have a value. So we have calculated this with the Excel file. Okay. And what we have to do now is to divide this value between 17 minus 0, because this is the, we need just U times okay, so how can we do it? On the Excel file, we have all the values here. Okay, so this is the heating load through the walls. This is the heating load through the floor, the heating load through the roof. And this is the heating load through the windows. And here we have the total thermal load through the walls, roof, floor, and windows. Okay, so if we click here, no, it's protected. But anyway, this is the result of the envelope. So this is 12,000. It's 12,912. We have to add the ventilation and infiltration loads. The ventilation is 11,787, and infiltration is 4,247. Vamos a ver si 17, 14, 2, 16, 1, 5 y 8, 13, 1, 3, 7, 10, 5, 6, 8. Okay, I don't know if I'm wrong, but this should be around 28,900 and this. Okay, so this is the heating load. So this is U times A times 70 minus 0. So what is the UA? It's 28,946 divided by 70. Okay, so this is 28,946 divided by 70. Okay, so this is 413. Around 400. So that's the value that we have to include in this UA. By default, we have 520. So that would be 413. You see what we have done? We have calculated the total heating load of the building, and then we have to divide by the difference of the temperature between indoor and outdoor temperature. Okay. So we can calculate this with the Excel file, or we can get this from Revit. In Revit, I showed you how to calculate the heating load. So we have the final value. We need to know the temperature difference, indoors minus outdoor temperature, and then we divide this by the temperature, and then we get the UA. Okay. Then the fuel, let's stick to gas. If we don't have any information about the efficiency, we can do this. What about the domestic hot water? Yes, because we have heating and domestic hot water. What is the domestic hot water usage? We can, Here we don't have any information about this. Well, we use the same option that you used here. Okay, the usage is 100 and something gallons. So you can use the same numbers that you did before. 100. The water temperature is 140. The environmental temperature, okay. The US value, okay. Now the number of collectors. What is the number of collectors? Now 6 is not going to be enough. The area of the panels should be the same. The slope, imagine that we have the same slope you had here, 30 something, okay. The orientation, it's always south, so this is 0, so we can leave all the values like that. So now we have the same demand of the domestic hot water plus the heating system. So 6, it's not going to be enough. Anyway, let's run and calculate. So you see that, well, yearly, we are close to it. We are around 0.3, it's 0.7. So I'm going to add 10 solar collectors. Okay, with 10 solar collectors, we are above 0.3, that's fine. And here we have, okay, let's plot, because I think if we plot, click here, monthly plot, and select heat, click OK. Okay, this is the heating load. It makes sense because in January is the highest, and then in June, July, August, we don't have any heating load. Makes sense, okay? What is this value? Let's check this. You see that here we have scale from 0 to 20. So this is around 12, 11 point something, 12, okay? Let's compare this to the heating load here. As you can see, we have the same profile, okay? But here we go up to 15. Okay, it's probably it's because here we have the operating hours per day. Here we have 5 days, 24 hours. If we have here 20 hours, probably that will be reduced. Yeah, so you see, so here the maximum value, it's between 10 and 15. And here the maximum value, it's around 12. So it's, so we have to check that the profile is similar, and it is. Okay, so we don't have heating here in June, July, and August. And the maximum value is in January, and the maximum value it's between 10 and 15. Okay, so here the maximum value it's around 12, so it's good. Okay, so we can check that with 2 different softwares we have the same results. So if that happens, means that it's good. Okay, so this is the heating load that we have. We can plot the domestic hot water use. And the domestic hot water doesn't have to do with the station. It's about the water use. So if we, so it depends on the number of days that we have in the month. February, it's always the lowest because we only have 28 days. Okay. But then we have 30, 31 days, 28, 31, 30, 31, 30, 31. It depends slightly on the outdoor temperature, but it's steady. Okay. So there's a difference between the heating load. The heating load, the maximum heating load is in January and December, and we don't have any heating load in summer, but the hot water consumption is steady throughout the year. And finally, we can plot the F value. And the F value, yeah, in the heating season, we have only like barely 20% of the needs, but here we have more than enough. Okay, so it's more than one. We might run the risk of overheating the system here, but well, I don't think so. And if it happens, it will happen only in July, probably. Anyway, it's not that bad. So I think 10 collectors is good, but we need to know that we have plenty of heat in summer, because in summer we only have domestic hot water, we don't have any heating system, and we have only 20%, less than 20% of the heat that we need in January or December. So we have to plot this. So yes. Okay, so we can copy these graphics, the F, the heating, and the domestic hot water use. Okay, so you have to copy these three elements here. And I think this is quite good. Okay, so we have already with first we have tried just this, the domestic hot water. Then we have added domestic hot water and the heating system. So first we need to know the amount of heat that we need, the power that we need in our system. So that's why we need to use another tool. We can use this one, we can use Revit, but we need a tool to calculate the heating system. And finally, yeah, we have to plot the amount of heat that we generate with our panels. Are we done? No, I want more. Okay, yeah, so I have all the hot water I need in summer, but I want more here. So I want to increase this element. What happens if I include more solar collectors? Instead of 10, let's say that we can have 20 solar collectors. If we have 20, I calculate again. And now the yearly is 0.5. Okay, so we are increasing. Let's do something crazy, 30. Okay, so if we have 30, now the average is almost 70%. Okay, so if I have 30 solar collectors, I am generating 70% or 68.5, almost 70% of the energy that we need throughout the year. What's the problem? That in these months, probably there will be an overheating, because if we plot this again, this has not changed. Okay, the heating loads have not changed. I have more panels, but I have the same heating load. I have the same domestic hot water load. What has changed is the F. Okay, so now we have 40% of the energy I need in winter, but for sure I will have an overheating problem there in summer. Okay, because that will grow, and probably there will be an overheating there. So what can I do? The third option, I can include a swimming pool on this schematic view. Okay. If I'm working with this, it seems the easiest way to work with, because we have only one boiler. So I'm going to include another option for this. So I'm going to connect this to a swimming pool. And what do I need? I just need to work with this. Copy. Okay, so I have these connections. That means that in winter, if I'm not using the outdoor swimming pool, we are talking about an outdoor swimming pool. In winter, I'm not using the swimming pool, it's empty. So I don't have this connection. So what it works is the connection between the tank and the radiant floor. But in summer, I don't need the radiant floor. So what I have is this connection. I think that the arrows are the other way around. There you go. Okay, so in summer, now it was good. Okay. So in summer, I'm doing all this. So all the heat that I don't need, I'm taking this heat to the swimming pool. So the swimming pool in summer will be warmer than usual. You might say, no, I want cold water in summer. Okay, it's up to you. But people in summer, especially here, it's not that warm. Okay, so if you go to a swimming pool that is at 70 Fahrenheit or 80 Fahrenheit, you say, oh, it's nice, believe me. So even having that in summer, having the opportunity of having a warm swimming pool in summer, it's a good feeling. So the excess of heat that we are generating with all the panels that we don't need, we are just taking that heat to the swimming pool. And how does that affect to my system? Let's find out here. Okay, remember that I needed 6 panels for the domestic hot water. Okay, so I have designed the domestic hot water and I had 6 panels. And now I have 30. So 24 panels are connected either to the heating system or to the swimming pool. Okay, because I don't want to run of domestic hot water in summer. So I have 6 panels for domestic hot water and 24 panels connecting either to the heating system or to the swimming pool. Okay, so now I have to change the system, and you see that we have a pool heating here. Pool heating. Okay, we're in the northeast, and now we have to design the pool. We have the pool surface area, and that's interesting because if we have a pool there's a swimming pool, and this swimming pool is filled with water. Okay. What's the temperature of the swimming pool? Let's say that the temperature of the swimming pool has to be 70 Fahrenheit. Comfort temperature. It's not too warm. It's not too cold. Just 70 Fahrenheit. We have connected this swimming pool to the solar collector. This is the solar collector. Okay, so we have connected somehow the swimming pool to the solar collector. So all the energy that we are gaining here, we don't need that energy because we don't have a heating system. But if we don't move this water, the system will suffer this overheating and it will burst. Okay, so we need to take this energy to an energy sink. So where I can release energy there and nothing happens because here we have a huge mass of water. So, but we are losing energy. This is a 70 Fahrenheit. And the outdoor temperature over the night is 60 Fahrenheit. We are losing heat. If the outdoor temperature is 90 Fahrenheit, we are gaining heat. But throughout the day, from 60 to 90, it's something common here. Okay, so sometimes we will be gaining energy from the sun or from the outdoor temperature, and sometimes we will be losing energy. So we can keep the temperature of the swimming pool at 70 Fahrenheit. Okay, so that's the strategy now. We can connect this somehow to the heating system. But in summer, we close this connection and then we connect the solar collectors to the swimming pool. We need a pool surface area. 540 square feet is not that much. What's the area of a swimming pool? Kind of. For a single family house, what would you say?
Probably like 15 by 30.
15 by 30 feet.
So for like a home
yeah, well, depending on your lot, but okay, 15 by 30. How much is it? 15 times 30. It's it's 400 up. So I was thinking in square meters. Okay, so 500. Let's type here 450. Okay, so 30 feet by 15. 450 square feet. What's the pool temperature? Well, here we can type. Let's start with 70 and see what happens. Okay. First month of the season, we don't want this heat to be in the swimming pool in January. So we can do that from, look at this. We start having problems in May until October. Okay. So let's say that the first month is May and the last month is October, because we have this graphic here. Okay, so from May to October, we have risks of overheating. The average pool depth, 5 foot average. Okay, that's fine. That's the average pool depth. Pool location, outdoors. This is important. Fuel. The system considers that you want to keep the pool temperature at 70. We don't want that. Okay, we just want to release the excess of the heat that we have. So that doesn't matter. It's fuel, gas. Okay. And we have okay. So I think we're done with this. Now we have the number of collectors. Now the number of collectors is not 30 because we need 6 for the domestic hot water. We just need 24. The collector area, collector slope. The slope is the same. Okay. Oh, the cover. That's interesting. If we cover at night, we can cover the pool. If we do that, we don't have heat exchange because at night the temperature will be lower than 70. so we won't lose energy. So that's the goal. Do we really want to keep the temperature at 70, or we just we don't mind? If we don't mind, don't use a cover, just select none and plot. Okay, that's it. So with 24 panels connected to this from May to October, we solve the issue. Okay, so we have the temperature of the swimming pool. If this is 1, that means that the temperature of the swimming pool will be 70. In June, July, August, and whatever, we don't need any auxiliary energy for that. And probably in May and October, we don't have enough heat to push the temperature of the swimming pool at 70 Fahrenheit. So what does it mean? We don't have any risk of overheating the system, because the excess of heat, we have released that heat to the swimming pool. Okay, the swimming pool gets to 70. Perfect. What if I type 80 here? And I calculate again. Okay, with 80, only in July, the temperature of the swimming pool will be 80. Okay, fine. I don't mind. But you know what I'm doing. Now the system it's not even more complicated. We only need a pipe connecting this to the swimming pool in summer. And then, okay, so here this works in winter and this works in summer. So it's not, we're not adding anything to the project, because we are adding just a few pipes, a couple of pipes going in and out of the swimming pool. We have to design a swimming pool, but this can be a part of the project. So that's why I told you that if you make a pool, pond or something a part of the project, because it's nice and everybody likes it. And we have a lot of examples from okay, everybody loves, it's el patio de los leones y el patio de los agallanes. Okay, everybody loves water, reflection. If we go to Mexico, we have Barragan. Okay, everybody loves water, especially when you have good weather. Everybody loves water. It's nice. It gives you a fresh. You feel fresh air when you are close to the water. You have the reflections, so everything is beautiful when you have water. And we have a lot of in Le Corbusier here. Okay, so it's a resource that architects have used many times because it's nice. Everybody loves water. So if you have a huge mass of water and you have this kind of protection, you can use this mass of water to release heat in summer. So not only is it beautiful, but it's worth it, because if you have this kind of solar collectors, the problem with solar collectors is the heat in summer. So you need something to release that heat in summer. So having a pond is the best thing that can happen. Okay. So I stop recording.